we're going to consider the moment of a force. And in general, you can think of this as a twisting force or a circular force. It's something a little different than just a plain force. And it's important because it affects statics, it affects free bodies, it affects the way that bodies behave and the forces applied to those bodies. So it's important for us to learn about and consider. You've most likely used a moment before, and students sometimes get confused because unfortunately the lingo is a little different. A moment is not a moment in time. That's not what we mean here. Think of a torque or a twist. That's really what we mean by a moment. After this lecture, you'll be able to understand and define what a moment is and then determine the moments of force in both two-dimensional and three-dimensional cases. As usual, there are, in particular, examples and group problems that you should go through in the slides. They'll serve as examples, but of course, I've recorded my own videos for you, and then there's a quiz as well that is taken from these slides. So I've removed those slides from my presentation, but they are present in the slides on the course website. So be sure to check those out as part of your study of this section. All right, so what applications are there for this thing called a moment? Well, if you look at a beam, so here's a beam that's just straddling, an opening in a wall, and it's supported very simply at either end. It's just sitting on the ends there, so it can actually rotate. When you apply the force in the center, what do you think is going to happen out at the end of the beam? If your answer is that it will rotate, you're right, because the beam is going to bend. It's going to deflect a little bit. The center is going to go down a little bit. It may not be enough for your eye to see, but it will happen. Any load on the beam will absolutely cause some deflection of the beam. Maybe not much, not enough to make a difference, but it's still there. It still exists. And more importantly, what happens is a moment ends up being generated within the material of the beam. And it turns out that the moment type of load, this twisting load that can exist within the beam, is actually more damaging to the beam than the direct force loads that are applied. But we'll study that in a later course. For now, just know that the effect of this force is a twisting. It turns out that the longer that moment arm is, the longer the distance dA between the support at the end and where the force F is applied, the larger the load, the twisting load inside of the beam will be. So it's really important to consider this and think about what are the ramifications of this load and how does this type of loading work. Now, that's not the only application. Something that's a little more concrete and intuitive is that we're talking about essentially just torque. That's really what we're talking about. And here's an example where a hammer is being used to pull a nail. If you ever try to grab a nail with a hand and pull it out of the wood, you didn't succeed unless you have a very rough hand. Even then, I don't think you could pull it out because so much force is required. So what a hammer does is it serves as a lever. Now, it's not just a simple lever like a seesaw where the loads are both directed straight down. Rather, a hammer has a force from a hand pulling on it, but the force from the nail is in a different direction. And yet, because the pivot point distance from O to FH is a longer distance than the distance from O to FN, there's a mechanical advantage here, and the amount of force required by the hand is less than the force that's actually generated to pull the nail out of the wood. Of course, you have to move the handle farther, and the nail will just barely come out of the wood, but this is basically a lever, and it works based on moments. There's a moment produced by the hand, there's a moment produced by the nail, and those two are, of course, in opposition to one another. But how would we model this? How would we calculate how much force is required by the hand if we, say, knew how much force is required to pull the nail out of the wood? That's what we're going to learn. So we're going to start off with a scalar formulation of the moment of a force. So you've probably turned a screw into something or tightened a bolt or done something with a fastener where you had to turn it either with a wrench or a screwdriver or some type of tool. And what you were doing is you were actually applying a twisting force, a circular force, so to speak, which we would call more properly the moment of the force being applied. And so the moment, the magnitude of the moment provides, how can I explain this? The magnitude of the moment is just as important in a static situation as a load itself. And in this particular case, you can calculate the moment by simply multiplying the amount of force being applied by the hand to the wrench by the distance between the point of application of that force to the center of rotation for this nut or whatever is being driven in. And of course, the longer the moment arm D, the less force will have to be applied because only so much torque is required to turn the fastener. So if you increase the moment arm, it's kind of like getting a cheater bar. If you've ever taken a tire off of a car, it's very difficult to use a single wrench to remove a lug nut, for example. They're very tight. They hold the wheels on your car very well, which is a good thing. That's what you want, right? But to get them off, what you really have to do, or what makes it easier, is to get a really long cheater bar. I've got a 4-foot bar I use all the time because it just makes it so much easier. I have to apply so much less force in order to turn the lug nuts off of the wheels of my car and remove tires and wheels and whatever I need to do. But understanding the concept of a moment, I think you probably have an intuitive understanding of it, but we're going to move all the way to a very mathematical formulation of it. So in the case of two dimensions, if we're looking at a situation from the top down here, the amount of moment, called m naught, is simply equal to the force that's applied to the body times the distance between the point of application of the force, or the line of the force, to the center of rotation. And that, in this case, is indicated by the symbol d. So simply F times d is the magnitude of the moment being applied to whatever body that this force is applied to, and is tending to rotate about that point. Now, one thing that's really important is to think about the sense of rotation. In this particular case, you look at it and you realize that force is tending to try to cause rotation in a counterclockwise sense. And so, I mean, if the force were pointed in the opposite direction, or if the force was in the same direction but on the opposite side of the pivot point, obviously the force would be causing a moment in the clockwise direction, opposite to what you see. And so one important point about that distance from the center of rotation to the line of action of the force is that it needs to be a perpendicular distance out to the line of action of the force. It's a really important point. The distance, the moment arm, always has to be perpendicular to the force. All right, so either we're going to end up with a clockwise or counterclockwise moment in the case of a two-dimensional moment situation, or moment loading situation. Now here's an example where we have a point O, and let's say we've got some arbitrary coordinate system such that B is vertical and A, the distance A, is horizontal. So B runs along the y-axis, A runs along the x-axis, and represents, distance out to the point of application of force F. If you want to calculate the magnitude of the moment of force F about O, which, by the way, you can calculate the moment of a force about any point you want on a body, but it usually makes the most sense to calculate the moment of the force about some useful point. And you'll see in examples what might be considered a useful point. Often a pivot point makes sense, or a pin in a bridge, or sometimes there's more clever places to choose. But anyway, you can choose any point you want. In this case, we've chosen O to calculate the moment of force F about O. In that case, we need the perpendicular distance between the line of action of F. Notice that's indicated by a diagonal dotted line moving up and to the right along the direction of F. We need the perpendicular distance from O to that line, and that's what lowercase d represents. So in this particular example, the magnitude of the moment of the force about O, or MO, is simply F times d. And of course, if you think about it, think about a circle about O that goes through the point where the distance intersects the force line of F. If you think about a circle there, F is tending to cause, in this sense, well, let's see, that's a counterclockwise rotation that it's trying to cause. It's always important to think about the direction of the moment when you're considering these things. Now, a lot of times finding that dimension d is a big pain and you'd like to avoid it. If you've already got a couple of dimensions along the regular coordinate system, like in this case, we have dimension b along the y-axis, dimension a along the x-axis, what you can do instead is break up the force into horizontal and vertical components, because if you think about it, A represents a horizontal moment arm for the vertical force component, Fy, Remember, that's a horizontal moment arm with a vertical force component, whereas B represents a vertical displacement or a vertical moment arm from O up to the line of action of Fx, where Fx is a horizontal force. So you see how the distance always has to be perpendicular to the force, okay? So since we've broken up force F into two components, we have two different perpendicular distances. Here's the beauty of this whole thing. If you calculate moment m naught based on Fy and Fx with these easy to figure out dimensions A and B, it'll be the exact same thing that you would have gotten by taking F times D in the previous figure. So this makes your life a whole lot easier, and all you really have to do is break down forces into their horizontal and vertical components. And that makes life a whole lot easier most of the time. So to calculate the moment, what would we do? Well, let's see. Notice that Fx is tending to cause a rotation about point O that is clockwise. You see that? Whereas Fy is causing or trying to cause a rotation about O that is counterclockwise. They're fighting each other, so to speak. If you need to pause the video and think about this for a minute, you should do it, because this is a really important point. Students get really confused about what is the distance that I need to use and how does this work. And one of the keys is to always remember, number one, that the distance, the moment arm itself, must be perpendicular to the force. One way to do that is to take the force and break it down into its components so you can use a vertical displacement like B with a horizontal component of force Fx and a horizontal displacement like A with a vertical component of force Fy. But notice they cause an opposite moment. We often consider a counterclockwise moment to be positive. There are reasons for that. I'll explain it a little later. But so in the equation, that's why Fy times A is indicated as a positive term, because Fy is causing a counterclockwise moment about point O, whereas Fx is causing a clockwise or a negative moment about point O with moment arm B. So be really careful about the signs on the two terms. And of course, you want to make sure that you're thinking clearly about how the forces or the components of forces will tend to cause rotation about the point where you're taking moments. Now, that's nice, but it turns out there's a mathematical tool, the vector cross product, which will do all this for you. I pointed out that in some cases it can be a pain to find the distances. What do you do if you have some just totally arbitrary distance in some weird direction, and you have a force in some odd direction? How do you calculate it? It can be really difficult to find the components of the moment arm in the x, y, and z, if we're talking about three dimensions, in the x, y, and z space, and the x, y, and z components of the force. But if you simply take the cross product, you'll get the same thing. So it's a more general method, and it's really the heart of the operation. So let me show you how that works. First of all, what the heck is a cross product? Well, it's pretty easy. When you take the cross product of two vectors, it's basically a way of multiplying vectors. It's not the dot product, it's the cross product. So we purposely use an X to indicate the cross product rather than a dot. We'll never abbreviate a cross product with a dot, okay? It's a different kind of multiplication with vectors than the dot product is. Anyway, so if you think about it, what are we doing here? Well, take your right hand, look at the figure on the page, point the fingers of your right hand in the direction of vector A. And then move your fingers in the way they would naturally close. Your fingers don't open the other way, right? They close this way. So move your fingers, rotate them in the direction they naturally want to rotate through the minimum angle possible, whatever that looks like. If you have to turn your head upside down or stand on your head or whatever you have to do, turn the fingers of your hand from pointing in the direction of vector A to pointing in the direction of vector B. And when you do that, when you point from A to B through the smallest angle in the direction that your fingers would naturally collapse, you'll find that your thumb points in the direction of the resulting vector of that cross product, in this case called C. So that's basically the right-hand cross product. So it helps a lot to think about this, and you'll see me use that quite a bit in examples. Now, be careful, because the cross product of B cross A is opposite to the cross product of A cross B, and you can see that because think about it. Put your fingers in the direction of vector B and turn your hand through the smallest angle you can find to get to A. Well, A is over here, right? So I got to turn my hand upside down, move through A, and guess what? my resultant vector is in the opposite direction to what it was before. So B cross A is a different thing than A cross B. They're related, they're just in opposite directions. So same magnitude, but opposite direction. It's also interesting to notice that the cross product itself can be computed as a magnitude and a direction. If you know the direction of C, so you can get a unit vector in the direction of that resultant vector C, then the magnitude is AB sine theta, which should sound familiar to you, or ring a bell, I guess. In the dot product, we used AB cosine theta. Remember that? So it's kind of interesting to see the symmetry here. But of course, in the dot product, we ended up with a scalar. We didn't tack on a u sub c, a unit vector, whereas in the cross product, we have to. So notice, interestingly enough, the resultant vector c, and therefore the unit vector in the c direction, is perpendicular to both A and to B. And that's how it's uniquely determined, because there's really only one vector, or one direction, one line, that will be mutually perpendicular to both vector A and vector B. Okay, so that makes some sense. We've seen a little bit about how to determine a cross product, but what about the unit vectors? Remember, there are unit vectors I, j, and k. This is a really useful right-hand rule tool, and you should try this. So you should try all 6 combinations of this. Let me describe them to you quickly. Take your fingers of your right hand, point them in the direction of the x-axis, okay? And then turn your fingers through the smallest angle to get to the y-axis. What you'll find is that your thumb points in the positive z direction, or the k direction. And therefore, I cross j is k. Now, on the other hand, if you were to take j and turn it into I through the smallest angle possible, it's a 90-degree angle because it's just a coordinate system. If you turn the fingers of your hand through the smallest angle, your thumb will point in the negative k direction. So I cross j is positive k, but j cross I is negative k. And remember, these cross products result in a vector. Now, I cross I is 0, because any vector crossed with itself is actually 0. I can show you that to you mathematically, but for right now, just remember that any vector crossed with itself, whether it's a unit vector or whatever it is, you will get 0 out of it. Or if you have 2 vectors that are different size crossed with themselves, as long as they're pointing in the same direction, you will still get 0. So any 2 vectors that point in the same direction, cross product of that is always 0. That's a useful thing to know. We'll use that in example problems. Now let's try some of the others. We've played with I and j. What about taking k and I? If we point our fingers in the direction of k, so straight up, turn our fingers through the smallest angle to get to I, what happens? Well, let's see. Our thumb points in the direction of j, doesn't it? So what we just discovered is k cross I is j. Now you should probably write all these down. I don't have them in a table for you, but there are 6 combinations of I, j, and k where you can take cross products and end up with either a positive or negative unit vector that's either I, j, or k. But anyway, so k cross I is j, but think about it. If you point your fingers, I'm trying to do this backwards on the camera, if you point your fingers in the direction of I and turn it into k, you'll find your thumb points in the negative j direction. So let's see. So k cross I is j, but I, trying to turn my hand around it, I cross k is negative j, okay? And you should be looking at the coordinate system and trying this out in your mind to make sure that you know how to do this. The last thing to talk about is starting with the jk combination. And so if you point your fingers in the direction of the j-axis, and turn your fingers through the smallest angle to get to k, you will find that your thumb points in the direction of I. So, in fact, j into k, or j cross k, is, make sure I got it right, I'm having to do it backwards for the camera. Yeah, make sure. What were we doing? J cross k, yes, is I. K cross j, though, is negative I. So you should write down all those combinations. Make sure you understand this. There is a circle you can draw with ijk, and it's just a brief description of this. Basically, if you go counterclockwise, I cross j is k, j cross k is I, k cross I is j. That's true. And if you go the other way, I cross K is J, K cross J is I, J cross I is K. I hope that's not too fast. Those are all negative, okay? So that's the wheel there is a nice way to write this down rather than writing down 6 different combinations. But however you can remember it once you figured it out and you understand it, write it down so that you know what's going on. Because you don't want to rediscover this later. You just want it to become second nature. Kind of like you don't have to think about 2 plus 2 is 4 anymore. That's the way this needs to be for you. So that's how you deal with the unit vectors themselves, but that's not really what we're interested in. We're interested in generally the cross product of 2 vectors, because what we really want to do is calculate the moment of forces. And it turns out that the position vector and the force vector, you can take the cross product of those two, and it turns out that that cross product is in fact the moment of that force with that moment arm. But we have to understand how to take cross products. And so you probably don't know much about linear algebra and matrices, but this is a matrix. You notice we've got I, J, K. We've got the components of A, B, and B, vectors A and B. So we've got AX, AY, AZ, BX, BY, BZ, written out in a matrix form. Okay, if that doesn't mean anything to you, that's okay. The bars on the side simply indicate that we're taking the determinant of that matrix. And what's being pointed out here is that the determinant of the matrix is, in fact, the cross product A cross B. That's some linear algebra stuff. Don't worry about it. Here's how you do it. Imagine canceling out a row and column every time you calculate one of the terms. So what you do, you say, okay, I want to deal with the I row column. So I'm going to calculate the moment that belongs in the I direction. Okay, so you notice what happens for the very first term here is we think of canceling out the first row and first column, okay, and we write where those two intersect, we write the vector I, the unit vector I, and then multiply it by AY times BX minus AZ, maybe I said that wrong, I'm sorry, AY times BZ minus AZ times BY. And you see that's written out here. Now that's not all of it. That's not all of the determinant of the matrix. There are 2 other terms to be included. It's kind of like foiling, but in a different way. So for the J element, imagine canceling out the entire first row and middle column. And so then we write negative J, remember that negative sign, because this is the odd man out, but mathematically you just have to put a negative sign there, so negative J, and then AX times BZ minus, come back the other way, AZ times BX, okay? The last term is the K term, so now we cross off the first row, last column. So we write K, because that's the unit vector that intersects, right? K, that's our unit vector, and we're calculating the magnitude along that direction of the moment of the force. We're going to do that in a minute. Right now it's just vectors. But then it's AX BY minus AY BX. And you can refer back to this slide as much as you like. I let students use slides on exams. I have no problem with that. I don't expect you to memorize all these things, but this will probably become second nature to you. But basically, it's from linear algebra, and all we're doing is calculating 2 by 2 determinants in order to come up with a total moment. So the last thing you do is you take all of these results, this I, negative J, K, all these results, you just add them together, and that's what we're doing. You don't just add them together where, you end up getting rid of I, J, and K. It's I times its term, it's scalar, minus J times its scalar, plus K times its scalar, and that's the result. So basically what we can do is if we have some general position vector to the line of action of the force or to the point of where the force is applied, in this case, we're interested in the moment of force F about point O. And so we draw the vector R, which has X, Y, and Z components, Rx, Ry, Rz, and the force vector as its components, Fx, Fy, and Fz. And to calculate the moment of that force about that moment arm, just take the vector cross product. Now you got to be careful because you got to remember this. It's not F cross R, it's R cross F. So it's position crossed with force, and both the position vector R and the force vector F have to be written in vector form, okay? So you can draw, if there's some convenient position vector from that origin where we want to calculate the moment about out to a different line or a different point on the line of action of the force F, that's fine. You can do that. Use whatever's easiest. But generally, you would simply use some vector that points to the tail of F, or as I said, any point on the line of action of F, and take the cross product R cross F, and you will get the moment of that force about the point that R begins at. Okay? So let's look at the cross product, and this is probably a little more useful because this is the form you'll actually use. This is not just the general definition of a cross product. Here in particular, we're calculating the moment of a force, which will end up being a vector because moments do have a direction. Now, it's a little bit confusing. Probably should have mentioned this early, but if you think about the direction of a moment, when you've got a wrench and you're applying force in one direction, you've got a moment arm in another direction, the moment itself is a twisting action that is perpendicular to both of those lines. I can't really draw it in the air with my hands here. You'll see it in example problems, but I use a double-headed arrow to indicate the direction of a moment. So if you think about a twist, how are you going to draw a twist force? Some kind of angled line with an arrowhead on it? Well, sometimes I do that, but more often what I'll use, because it's very clear, is I will use an arrow with two heads on it, and that arrow, instead of pointing in some rotational direction, let me do it this way. Instead of pointing in some rotational direction, it'll point, my thumb then is the double-headed arrow that indicates the twist. Okay, so to figure out what I mean by, if I draw a double-headed arrow at the board and you're trying to figure out, well, how is that twisting the body? Well, point your right thumb in the direction of that double-headed arrow, and the way your fingers rotate, that's the way the twist is going, okay, or that's the way the moment is going. So again, expanding this equation by using 2x2 determinants, using the method that I showed you earlier, this is how it would expand out. We'd have, Ry times Fz minus Rz times Fy in the I direction. That's the I direction component of the moment, the resultant moment. And sometimes it'll be 0, sometimes it won't. Same with J and K. And then you can read the rest of the equation. Notice the negative sign, though, just before the J term, comes from the mathematics of it, that you have to have a negative sign there. Now, it could be that the terms inside of those brackets ends up being negative, and then negative times negative is positive, and the component of the moment in the J direction is a positive thing in that case. But by default, assuming that the items inside of all of these parentheses ends up positive, we'd have a positive I, a negative J, and a positive K component of the moment M naught. And you might want to verify by, pausing the video and expanding that matrix yourself with 2x2 determinants to make sure that this equation's right. I guarantee it is, but you need some practice, so why don't you give that a shot? So what's nice about this is that the physical meaning of this cross product is that you get a moment out of it. So you get the moment of the force about whatever point R comes from.